Digital signal processing. Digital signal processing is the use of digital processing such as by computers or more specialized digital signal processors to perform a wide variety of signal processing operations. So what I'm telling you is that a computer basically is a digital signal processor device. The signals processed in this manner are a sequence of numbers that represent samples of a continuous variable in a domain such as time, space, or frequency. Digital signal processing and analog signal processing are subfields of signal processing. DSP or digital signal processing applications include audio and speech processing, sonar, radar, and other sensory array processing, spectral density estimation, statistical signal processing, digital image processing, signal processing for telecommunications, control systems, biomedical engineering, seismology, among others. Most of the people is talking about data, but most of them they cannot understand basically what it means. Remember that data is a current or a voltage, a sample or a current or a voltage. When I say a sample is whatsoever quantity, whatsoever reality that can be measured. Scientists already have created the way in order to understand a current or a voltage. Any kind of current or voltage sample is divided into several bits or chunks of electricity. Those chunks of electricity has a length of 0.577 milliseconds. They created traffic, or they travel at in intervals of 4.616 milliseconds. If you multiply 4.616 milliseconds times 0.577, the result will be 8, and that's the reason why the computer system use a binary system in order to calculate their mathematical system. Digital signal processing can involve linear or nonlinear operations. Nonlinear signal processing is closely related to nonlinear system identification and can be implemented in the time, frequency, and spatio-temporal domains. The application of digital computation to signal processing allows for many advantages over analog processing in many applications, such as error detection and correction in transmission, as well as data compression. DSP is applicable to both streaming data and static or stored data. To digitally analyze and manipulate an analog signal, it must be digitized with an analog to digital converter. Sampling is usually carried out in two stages: discretization and quantization. Discretization means that the signal is divided into equal intervals of time, and each interval is represented by a single measurement of amplitude. Remember that I told you that each interval has a length of 0.577 milliseconds. Quantization means each amplitude measurement is approximated by a value from a finite set. Rounding real numbers to integers is an example. The Nyquist-Shannon sampling theorem states that a signal can be exactly reconstructed from its samples if the sampling frequency is greater than twice the highest frequency component in the signal. In practice, the sampling frequency is often significantly higher than twice the Nyquist frequency. Theoretical DSP analysis and derivations are typically performed on discrete time signal models with no amplitude inaccuracies, quantization error, created by the abstract process of sampling. Numerical methods require a quantized signal, such as those produced by an analog digital converter. The processed result might be a frequency spectrum or a set of statistics, but often it is another quantized signal that is converted back to analog, fed by a digital to analog converter. Domains. In DSP, engineers usually study digital signals in one of the following domains: time domain, which is one-dimensional signals; spatial domain is multidimensional signals; frequency domain and wavelength domains. They choose the domain in which to process a signal by making an inferred assumption or by trying different possibilities as to which domain best represents the essential characteristics of the signal and the processing to be applied to it. A sequence of samples for a measuring device produces a temporal or a spatial domain representation, whereas a discrete Fourier transform produces the frequency domain representation. Time and space domains. The most common processing approach in the time or space domain is enhancement of the input signal through a method called filtering. Digital filtering generally consists of some linear transformation of a number of surrounding samples around the current sample of the input or output signal. There are various ways to characterize filters. For example, a linear filter is a linear transformation of input samples. Other filters are nonlinear. Linear filters satisfy the superposition principle. For example, if an input is weighted linear combination of different signals, the output is a similarly weighted linear combination of the corresponding output signals. A causal filter uses only previous samples of the input or output signals, while a non-causal filter uses future input samples. A non-causal filter can usually be changed into a causal filter by adding delay to it. Number 2, a time-varying filter has constant properties over time. Other filters, such as adaptive filters, change in time. Number 4, stable filter produces an output that converts to a constant value with time or remains bounded within a finite interval. An unstable filter can produce an output that grows without bounds, with bounded or even zero input. And finally, a finite impulse response filter uses only the input signals, while an infinite impulse response filter uses both the input signal and the previous samples of the output signal. Final impulse response filters are always stable, while infinite impulse response filters may be unstable. A filter can be represented by a block diagram, which can be used to derive a sample processing algorithm to implement the filter with hardware instructions. A filter may also be described as a different equation, a collection of zeros and poles, or an impulse response or a step response. The output of a linear digital filter to any given input may be calculated by convolving the input signal with the impulse response. Frequency domain. Signals are converted from time or space domain to a frequency domain, usually through use of the Fourier transform. The Fourier transform converts the time or space information to a magnitude and phase component to each frequency. With some applications, how the phase varies with frequencies can be a significant consideration. Where phase is unimportant, often the Fourier transform is converted to the power spectrum, which is the magnitude of each frequency component squared. The most common purpose for analysis of signal in the frequency domain is analysis of signal properties. The engineer can study the spectrum to determine which frequencies are present in the input signal and which are missing. Frequency domain analysis is also called spectrum or spectrum analysis. Filtering, particularly in non-real-time work, can also be achieved in the frequency domain, applying the filter and then converting back to the time domain. This can be an efficient implementation and can give essentially any filter response, including excellent approximations to breakwall filters. There are some commonly used frequency domain transformations. For example, the Cepstrom converts a signal to the frequency domain through Fourier transform, takes the logarithm, then applies another Fourier transform. This emphasizes the harmonic structure of the original spectrum. Zulu plane analysis. Digital filters can in both infinite or finite types. The finite types filters may have many advantages, but are computationally more demanding, whereas finite impulse filters are always stable. Infinite filters have feedback loops that may become unstable and oscillate. The Zulu transform provides a tool for analyzing stability usages of digital infinite filters. It is analogous to the Laplace transform, which is used to design and analyze analog infinite filters. In numerical analysis and functional analysis, a discrete wavelet transform is any wavelet transform for which the wavelets are discretely sampled. As with other wavelet transform, a key advantage is it has over Fourier transform's temporal resolution. It captures both frequency and location information. The accuracy of the joint time frequency resolution is limited by the uncertainty principle of time frequency. Applications. Applications of DSP include audio signal processing, audio compression, digital image processing, video compression, speech processing, speech recognition, digital communications, digital synthesizers, radar, sonar, financial signal processing, seismology, and biomedicine. Specific examples include speech coding and transmission in digital mobile phones, room correction of sound in hi-fi and sound reinforcement applications, weather forecasting, economic forecasting, safety data processing, analysis and control of industrial processes, medical imaging such as CAT, scans, and MRI, MP3 compression, computer graphics, image manipulation, audio crossovers and equalization, and audio effects units. Implementation. DSP algorithms may be run on general-purpose computers and digital signal processors. DSP algorithms are also implemented on purpose-built hardware such as application-specific integrated circuits. Additional technologies for digital signal processing include more powerful general-purpose microprocessors, feed programmable gate arrays, digital signal controllers, and stream processors. For systems that do not have real-time computing requirement and the signal data exists in data files, processing may be done economically with a general-purpose computer. This is essentially no different from any other data processing, except DSP mathematical techniques are used, and the sample data is usually assumed to be uniformly sampled in time or space. An example of such an application is processing digital photographs with software such as Photoshop. When the application requirement is real-time, DSP is often implemented using specialized or dedicated processors or microprocessors, sometimes using multiple processors or multiple processing cores. This may process data using fixed-point arithmetic or floating point. For more demanding application, field programmable gate arrays may be used. For the most demanding application or high volume in products, ASIC might be designed specifically for the application. Techniques for DSP, we can say are bilinear transform, discrete Fourier transform, discrete time Fourier transform, filter design, Gersel algorithm, LTI system theory, minimum phase, S-plane, transfer function, and Zulu transform. In the future video clips, we will be explaining the meanings and the application of such subjects. By the time being, thank you very much. See you next time.